Suppose you create an array that can hold 4 names and you fill it completely. Now you need to add a fifth. A regular array has a fixed size chosen when it is created, so there is no room and you cannot simply make it bigger. So how do we get an array that grows whenever we need it to? That is exactly the problem a dynamic array solves. And by the end of this video, you will understand exactly how it works inside. A dynamic array is an array that automatically grows as you add more elements. In Java, this is the array list. In Python, it is the built-in list. You still get the two things arrays are great at: storing elements in order and reading any element instantly by its index. But you no longer have to know the size in advance. Here is the key difference. A fixed size array locks its length the moment you create it. If it is full, that is the end. A dynamic array does not lock its length. When it runs out of room, it quietly makes itself bigger, so from the outside it feels like an array that never fills up. To do this, a dynamic array keeps two separate numbers. Size is how many elements you have actually added, what you see and use. Capacity is how many elements the underlying storage can hold before it must grow. Size is always less than or equal to capacity. The gap between them is just empty, reserved space waiting to be filled. Underneath, a dynamic array is still a normal array, one continuous block of memory, with every element the same size, sitting right next to each other. This detail matters because it is the reason the next operation is so fast. To read the element at a given index, the array does a single calculation. It takes the starting address and jumps forward by the index times the size of one element. It does not walk through the other elements. It lands directly on the one you asked for. So reading by index takes constant time, O of 1, no matter how large the array is. Updating a value works the same way. To change the element at an index, it jumps straight to that spot and overwrites it. No shifting, no searching. Updating by index is also O of 1. The most common operation is adding to the end. The array places the new element in the next free slot and increases the size by 1. As long as there is spare capacity, this is instant, O of 1. But what happens when the array is full and you add one more? It cannot stretch the existing block because the memory right after it may already be used. So it allocates a brand new, larger block, copies every existing element across, adds the new element, and switches to using the new block. How much bigger does it get? Not just one slot, that would mean copying everything on almost every add. Instead, it grows by a constant factor. Python's list and Java's ArrayList grow by roughly 1.5 to 2 times the current capacity. The old, smaller block is no longer needed, so it is automatically cleaned up by garbage collection. And note, dynamic arrays usually grow but do not automatically shrink, so removing elements frees the slots but keeps the capacity. Now, copying everything during a resize clearly costs O of n for that one step. So how can we say adding to the end is fast? Because resizes happen rarely and get rarer. Each time the capacity doubles, you can add twice as many elements before the next resize. If you spread the occasional expensive copy across all the cheap instant adds in between, the average cost per add is still constant. We call this amortized O of 1, costly rarely, cheap mostly. Adding to the end is cheap, but inserting elsewhere is not. To insert at the beginning or the middle, every element from that position onward must shift one step to the right to open a gap. In the worst case, inserting at the front, almost the entire array moves. So inserting anywhere except the end takes linear time, O of n. Removing follows the same rule. Removing the last element is instant, but removing from the front or middle leaves a gap and every element after it must shift left to close it. So removing from anywhere except the end is also O of n. What if you do not know the index, and you only know the value you are looking for. Then the array has no shortcut. It must check elements one by one from the start until it finds a match or reaches the end. Searching by value is O of n. If fast membership checks are what you need, a hash set from our earlier video is the better tool. One more thing students always ask: what if you use an index that does not exist, like index 10 in an array of size 4? The dynamic array does not return garbage. It immediately stops with an error, an index out of bound exception in Java, or an index error in Python, which protects you from reading memory that is not yours. Let us put it all together. Access by index and update by index are O of 1. Adding to or removing from the end is amortized O of 1. Inserting or removing at the front or middle and searching by value are O of n. These few facts are enough to reason about almost any list-heavy problem. You might wonder how this compares to a linked list. A dynamic array stores everything in one continuous block, which makes index access instant but middle inserts slow. A linked list stores separate nodes connected by links, which makes inserts at a known position fast but index access slow, because it must follow the links one by one. They are mirror images, and we will explore the linked list in the next video. So when should you reach for a dynamic array? Use it when you need an ordered collection, fast access by index, and the freedom to grow. Avoid it when you do constant inserts and removals at the front or middle. A linked list or a DQ fits better. Or when you only care about membership, where a hash set wins, or when the size is fixed and known, and you need maximum performance, where a plain array is enough. A simple real-life example is a music playlist. You keep adding songs to the end and the list just grows. You never declare its final length in advance, and you can jump straight to any track by its position. That is a dynamic array in everyday use. Let us see it in code. In Java, we use ArrayList. We add to the end, read with get, update with set, insert at an index, remove, and check the size. In Python, the built-in list does all of this with the same ideas: append, indexing, insert, remove, and len. Two quick tips. In Java, if you know roughly how many elements you will store, pass an initial capacity to avoid repeated resizing. And in both languages, accessing an index outside the current size raises an error. So check your bounds. So, to summarize, a dynamic array is a resizable array built on top of a normal one, tracking size and capacity. Access and update by index are instant. Adding to the end is fast on average because it grows by a constant factor and copies only occasionally. Inserting, removing, and searching in the middle take linear time. Choose it when you need an ordered, growable, index-friendly list. If this helped it all make sense, please subscribe for more visual explanations. Next up, the linked list explained visually.